So, good morning. I am Krishna Kumar from Krishna's classroom. So, we look at Riemann integration further and recall some of the examples we have looked at. And the last thing that we considered was the problem of interchange of limiting process and the integration. Now, this is not something that can be taken for granted, as we have a couple of examples to highlight this point. Look at the first one, which we have already considered, where a sequence of functions fn has been defined as fnx equal to n e power minus nx for x belonging to 0, 1 and n equal to 1, 2, 3, etc. Then one observes that it's a nice continuous function which takes the value n at x equal to 0, and then it's a continuous function on the interval 0, 1. Therefore, every fn is a Riemann integrable function. For each n, this is true. Now we look at the pointwise limit of this, and that's easy to compute. Now you see that limit n tends to infinity fnx equal to f of x, we define this way. Now you see that x belonging to the open closed interval, that is open at the point 0 and then the interval 0, 1, that is 0 is not included. At all other points the function converges. Where does it converge to? Now you see that the function, the limiting function is that the following. I think I have not put it here. So it converges to f of x equal to what you have at 0, it is equal to n, and at all other points it is 0. Zero for x belonging to and limit n tending to infinity fn at 0 equal to does not exist, because it's a divergent sequence that you have. Okay, that's quite easy to see. Now look at this. So the function that you get is or if you look at the integral of fnx on the interval 0 to 1, where it is Riemann integrable, you can compute this, and this is equal to 1 minus e to the power minus n, and this goes to 1 as n tends to infinity. But f is not defined as a revalued function at x equal to 0. Sorry, real valued function at x equal to 0. Hence f does not belong to is Riemann integrable on the interval 0, 1. So what we have seen is that the sequence of functions Fn converges everywhere except at 0 on the interval 0 to 1. And the integral of Fnx dx converges integral 0 to 1 converges to 1 as n tends to infinity. However, f is not defined as a real valued function at x equal to 0, and hence the limiting function is not a Riemann integrable function on the interval 0, 1. Therefore, here we cannot conclude that limit n tending to infinity integral 0 to 1 fnx dx, which is equal to 1, and this is not equal to integral 0 to 1 fx dx, which is not defined at all. So one of the questions that we were asking is why this happens. Okay, we take the next example and then together we make some remarks. So the next example is also more or less of the same type. So what you have is, you know that the set of all rational numbers form a countable set, and especially on the interval 0, 1. So we consider the interval 0, 1 and we look at the rationals on the interval 0, 1 and we can enumerate them. We can enumerate them as R1, R2, etc. and so on. It's a countable collection. Now we define the function fnx to be equal to 1 for x belonging to R1, R2, etc. Rn, and 0 elsewhere on the interval 0, 1. Okay, that's the definition of Fn. Now we will examine in detail what this function is and what the limits that you get. Then you see that each Fn is a Riemann integrable function on the interval 0, 1. The reason being that the function has discontinuity only at finitely many points. It is 0 everywhere except at finitely many points. And therefore it's a Riemann integrable function. So you can look at you call the limit as n tends to infinity fnx to be equal to f of x, and one can observe that fx is equal to 1 for x belonging to q intersection 0, 1 and is 0 for x not in the complement of this on the interval 0, 1. That we will examine, and it's nice to examine this. Okay, then you see that integral 0 to 1 fnx dx is 0 because it is everywhere except at a finitely many points. The function is 0, therefore it is 0. However, the function f that you get as a limiting function is not a Riemann integrable function because it is the characteristic function of q intersection the interval 0, 1, which you already know is the Dirichlet function, which is not Riemann integrable. And you have already examined that, because you get the upper sum and lower sum different, and upper integral and lower integral different, and so on. So that we have analyzed in detail earlier. Therefore, in this case also you see that limit n tending to infinity integral 0 to 1 fnx dx is not equal to integral 0 to 1 fx dx, and this integral does not exist. That is the reason. Again, we ask the question why. Or the pertinent question is this: under what conditions we can say that the interchange of limiting operation and integration is permissible? Okay, with the integration being in the sense of Riemann. Okay, that's the question. So we look at the third example. The third example, you have fnx equal to x to the power n. If you try to plot the graph of this is very simple. Okay, so what you have is 0 to 1, 1. So you see that this is f1, this is f2, this is f3, and so on. So it will start bending towards this. And eventually what happens is, in the limit, this sequence of functions go to 0 on the interval 0 to 1, except at the point 1. At 1 it is a constant sequence and it's equal to 1. Okay? So it goes to a discontinuous function. Nevertheless, there is discontinuity only at one point. So all the fn's and f are Riemann integrable, and you can compute the Riemann integral of fn, integral 0 to 1 fnx dx is equal to 1 by n plus 1, which is tends to 0 as n tends to infinity. So limit n tending to infinity, integral 0 to 1 fnx dx is equal to 0. On the other hand, integral 0 to 1 fx dx is also equal to 0, because that function is 0 everywhere except at a point. Okay? So in this case, the interchange of limiting process and the integration takes place. Okay, so I think we examine in some detail the second example, which we shall meet here. Now in this context, we also proved one theorem, or at least outlined the proof of one of the theorems that is concerned about the interchange of integration and the some limiting process. So let us look at this. So the theorem that we have proved is this. Let me just recall this. Let be a sequence of Riemann integrable functions . Riemann integrable functions on A. Let the sequence Fn converge to a function f uniformly then f is Riemann integrable and limit n tending to infinity integral 0 to 1 integral 0 to 1 limit n tending to infinity, which is equal to integral 0 to 1 That means the interchange of limiting process and the integration is valid. And the condition that you need is something about the mode of convergence. It says the convergence should be uniform. So you assume that Fn converges uniformly. If Fn converges uniformly, then the interchange of then the limiting function is Riemann integrable. Not only that, the interchange of limiting process and the integration process is valid. Okay. So what we need is to examine our examples where this fails to hold, and you naturally come to the conclusion that possibly it is the uniform convergence that breaks down. So let us look at the two examples that we have looked at. And you see that in the first example, the function that you have is fnx equal to n e to the power minus nx for x belonging to 0. Okay? And what happens with the fx? Fx is equal to 0 for x belonging to 0, 1 and does not converge at all. So f is not defined at x equal to 0. Why it is not defined? You see that fn 0 is actually equal to n. So what happens? It just shoots up. Okay? It's a monotonically increasing sequence and diverges. That's the problem. Okay? And elsewhere you see that n e power minus nx as n tends to infinity goes to 0. And this is quite an interesting thing that you have to be aware of. So this is generally associated with this general result that px e to the power minus x limit where p is a polynomial in x. Now this is the general result which you should try to work out. Okay. So what happens is the polynomial has a growth at infinity. But what happens is e to the power minus x goes to 0 very rapidly. And in fact, what happens is that the growth of px at infinity and the growth of e to the power x at infinity are such that e to the power x shoots off much faster to infinity than any polynomial of any degree px. Okay, so this is a general result, and you can connect this with this particular one, because here of course n it's a discrete a sequence through which it goes to infinity. So it is n that goes to infinity. Okay, fine, right. So let us, so that's about it, and therefore you see that what happens here is that the function fails to be uniformly convergent, because what happens is at 0 the function shoots up, it doesn't converge at all, right? But the second example is very fascinating, so we will look at this. The second example, now we will try to examine more closely, right? And in this case it is quite easy to prove that it is not uniformly convergent. That's not it. The second example we will try to work out in detail. see that here Fn is, let me do the following. Okay, so let me mark the sequence of functions. And we take x belonging to q intersection q complement intersection 0, 1. That means at all irrational points. Okay. Now you see that by definition, you see that the function takes the value 0 at any x. So I am just taking x as a general point of this class. This is what we have. And you see that at those points the function converges to 0. So that's rather something that we observe. It is interesting to see what happens at this. Now we look at the enumeration of the points R1, R2, etc. of the rational points. So we list it out. What does this look like? See, you look at F1 R1. Okay? F1 R1 equal to 1 and 0 at R2, R3, etc. So you have the value of the function F1 is 1, etc. What about F2? F2 is equal to 1 at R1, at R2 it is 1 and 0, etc. And what happens? Fn is equal to 1 at R1 and 1 at R2 and 1 at R3, etc. 1 at Rn. Okay, and then if you write here Rn plus 1, then you see that this is 0, 0. Etc. etc. So what do you get? See, at R1, the sequence F1 R1, F2 R1, etc., Fn Rn, etc. is a constant sequence, namely the value taken as 1. At R2 also, the first term, that is F1 R1 is F1 R2 is equal to 0. F2 R2 is 1, and from then on it is 1, therefore you get this going to 1 again. And similarly for all other points, at R3 also it goes to 1. And you see that in general at Rn and Rn plus 1 it goes to 1, because what happens is you get the only values it takes up is either 0 or 1. So in the first several terms it is 0. And then the entire tail is equal to 1. Therefore, all these things converge to 1 at R1, R2, etc. Rn plus 1. Okay, so this is the scenario that you have there. Therefore, the limiting function is 0 everywhere except at the irrational points, and it is equal to 1 at all rational points. So that is how fx is defined, and you know it is not a Riemann integrable function. Now once again, if you apply the previous theorem, see here the limiting function is defined It's a well-defined function. But it's not Riemann integrable. Why it should fail to have the Riemann integrability? Because each of these functions, f1, f2, etc., are all Riemann integrable functions on the interval 0, 1. But f is not Riemann integrable. Why it fails to be Riemann integrable? That is quite clear the way in which it is defined. And what happens to your theorem? So necessarily, I think you should have something going wrong with your limit, okay, with the convergence, okay, and one should get that the convergence in this case is not uniform, okay. So let us examine this point. Now I am doing this mainly because you should learn to examine these kind of things in detail. In fact, without putting your hand on good examples, you will not learn mathematics, and you should know how to do this. In fact, it's quite a nice. I mean, if you are very keen on doing mathematics, one has to do it, and you should also learn to enjoy this. Okay, so let us examine why this is not uniform convergence. Now that is the next question. So we conclude that possibly Fn does not converge uniformly. On the interval 0. In fact, that must be the reason. Otherwise, the limiting function, although the limiting function is well defined, unlike the first example, defined on the whole interval 0 to 1, but you see that it's not Riemann integral. Okay? So, in the light of the theorem that we have proved, there should be something going wrong with the uniform convergence. Okay, let us examine what is uniform convergence. Go to the definition. Fn converges to F uniformly on 0, 1. You can replace this by any interval. If given epsilon positive, there exists n epsilon such that for every n greater than n epsilon and for every x belonging to 0, 1, mod Fn x minus fx is less than the definition. See, in general, it's a precondition that Fnx should be converging to Fx, that is, it is pointwise convergent. And what will be the corresponding definition of the pointwise convergent? It will be Fnx converges to f of x on f of x for x belonging to 0, 1 if given epsilon there exists an n, and this n could be dependent on both epsilon and x such that for every n greater than n epsilon, mod Fnx minus fx is less than epsilon. Okay, but it becomes uniform convergence, which says that given epsilon there exists an n independent of the point x that you choose on the interval. Okay, that's the important. That's why I have specifically written here n depends only on epsilon and not on x, such that for every n greater than n epsilon and for every x belonging to 0, 1, this inequality goes. Therefore, what do you mean by the negation of this? Okay, so let us examine that. What about the negation? So, what we are looking for is this: Fn converges to F not uniformly on. So some of these conditions could fail. Okay, one of the conditions that could fail is Fn may not converge, Fn x may not converge at all at some x belonging to 0. This is one possibility. Either this or the second possibility is that Fnx converges for each x, that is, the sequence Fn converges pointwise, but not uniform. What does it mean? It means the following. See, it's a negation of this statement. What will be the negation of this statement? Negation of this statement is there exists some epsilon positive such that for every n there exists some n greater than n and some x belonging to the interval 0, 1 such that mod that's the negation. So there exists some epsilon, so you should be able to find some epsilon for which for every n you should be able to find some n greater than n and some x over the interval 0, 1 such that this is. Let us see whether it works, how it works in this example. Now let us see this. Okay, we fix n because it should be true for every n. So there should be some n. So we choose an arbitrary n. So let us choose this here. So let me write here f of. What is f of n? F of n is 0 here, 0. Sorry, 1 here, 1 here, 1 here, etc. 1 here, up to Rn plus 1, up to Rn it is 1 and 0 beyond that. Okay, so this is what. Okay, Now what happens at the point Rn plus 1? At Rn plus 1, see that all this becomes 0, this also becomes 0, and this also becomes 0 for Rn plus 1, and from then onwards it is 1 multiplication. Okay? So what do you do? So we fix n. Now we have to exhibit. Okay, let us choose. First we choose so there exists yeah, what is it? Fn converges to f like this. So for some epsilon positive that we have chosen, for half epsilon equal to half, we show that this goes wrong. And for every n, so we choose n arbitrarily and fix it. We want to exhibit that there is some x over the interval 0, 1. So, and some n greater than the particular n for which this is greater than epsilon. So let us take n to be equal to n plus 1. And x to be equal to, or you can write here, say n plus 2, and x you choose as r. Now compute this. So what do you get? You get f of n plus 2 r n plus 1 minus f of and a point x to be equal to Rn plus 1, where f of n plus 2 and also an n greater than, a small n greater than capital N, such that this is true. That's what we have. Okay, therefore it doesn't converge to this. Okay, so you examine this carefully. So it's a uniform convergence that fails to happen, right? Now we take up the third example. The third example we have looked at. See, everything is fine. It's a positive example. It's not something to negate the result. It's not a counter example in that sense. What you have here is the function x to the power n, and I think I have described this, and where the interchange of integration and the limiting process is valid. Okay, so third example complies with the case, and you see that in this context we have the following theorem. You see that this is this result due to R cell says, you can look up the proof of this in some book. So this is the sort of bounded convergence. We are talking about the bounded convergence. Okay. So let the sequence Fn be a sequence of Riemann integrable functions on AB such that for some m positive mod fn x is less than m. That means all these functions fn are bounded by a constant. Okay, so it's a bounded class of functions that you are talking about. And the functions are all Riemann integral. That's the assumption that we made. So the assumptions are Riemann integrable functions. It's bounded. These are the two assumptions that we made. And we also assume a third assumption, namely that let fnx converge to fx pointwise. For every x belonging to AB, and let f be Riemann integral. So we have a third assumption creeping in, namely the function f is also Riemann integrable on AB. Then limit n tending to infinity that means the interchange of limiting process and integration is valid. Okay. Now let us examine. I leave the proof of this to you to work it out, and it cannot be. It's not really difficult to work it out. So what are the assumptions that you need? The fns are all Riemann integral functions. They are bounded by a constant m. They are all bounded functions bounded by the same constant. And then the third assumption is that limit of this, the limiting function is also Riemann integral. Okay. So if you compare this theorem with the previous theorem, you assumed uniform convergence. Riemann integrable functions with uniform convergence, then you concluded from that the limiting function is Riemann integrable and the interchange of limiting limit and the integration is permitted. Now let us examine our examples in the light of this new theorem, because those examples where everything fails, this fails to the interchange is not permitted, something should be going wrong in the light of this theorem also. First of all, you see that in the first example you had this function, that is fnx equal to n into e to the power minus nx or x belonging to. Okay. So this sequence of functions, you see that there does not exist an m such that mod fnx is less than m for every x belonging to AB, because what happens is, if you choose an m, you can always find out, look at f m plus 1. F m plus 1 at 0, x is just overshoots that bound. So it fails, this one fails to hold in the first example. So there is no question of proceeding any further. It is bound to fail, or it is rather failing because of that. In the second example, you see that everything is fine. These functions, the functions take only values 0 and 1, therefore the functions are all bounded. Okay? F and x is bounded by 1. So you have 0. In the second example, what you have is, in the second example, what you have is that 0 less than or equal to f and x less than or equal to 1. So there is an error. There is no problem with this. Then we found that in the light of the previous theorem, it fails because of lack of uniform convergence. Okay? Right? So what is the factor that fails here? See, this is where you need an additional condition, that the limiting function that you get should be Riemann integrable, and it is not Riemann integrable in the second case, therefore it fails to, the third condition actually does not hold, therefore the interchange is not permitted. Okay? So that is that. Now if you look at the third example, in the third example you see that all these conditions are valid. It fits into the frame of both these results, and therefore you have, okay, it fits into the frame of the second, certainly Arzel's theorem, because what you have is the Fn is x to the power n, and Fn converges for every x belonging to the 0, 1, and this is Fx is 0 everywhere except at 1, and at 1 it is equal to 1, and it's a Riemann integrable function, and this happens. You see that these functions are all bounded by 1. Okay? And secondly, the limiting function is a Riemann integrable function. And all these are the Riemann integrable functions. Therefore, the interchange of integration and limiting process is valid. But you can try to work out the proof of this as an exercise, or you can look into some book on Riemann integration where the proof is worked out. Okay, but all the more better if you try to put your hand on this. Yeah, okay. But certainly we are going to have these similar theorems once we do Lebesgue integration theory. We will have a look at it at that time in some detail. Right? And all these discussions that we make right now becomes redundant, because what happens is that that all Riemann integrable functions are Lebesgue integrable, and then this theory will be completely superseded by the Lebesgue integration theory. So this is an exercise to find the path of evolution of the ideas, and that is essential for a learning mathematician, somebody who is getting trained to be a mathematician. Okay, at the learning process, it's not the ultimate result that matters here, but the process of really doing it. Okay. Now we take up another problem. The next question that we take up is that of what we call completeness of the space. What exactly do we mean by complete space? You know that in mathematics, one deals with different spaces, which happens to be the playing ground to analyze mappings and functions. So you will have one space with a particular structure and the other one with a specific structure, and we will be looking at mappings from here to here. And what we want to analyze is how this mapping behaves, or what properties are inherited by the basic properties of the domain space and the range space. In fact, what happens is many problems from other areas like physical sciences or even social sciences, when formulated mathematically, will be reworded in the language of mappings between different sets, and quite often the sets with certain very specific structures. And it's the interplay or how these structures play a role in having a result or having to justify some of the observations that you make. Well, this is a concern of mathematicians. Therefore, you are interested to know some of the structural features of certain spaces. Okay? So, one of the problems that you encounter is, see, you have a space X with certain structure and a space Y, and you have got mappings from here to here. Right? A lot of questions are asked about the properties, how the properties of F of X and Y influence the properties of F, or even a collection of functions here, and then how they are influenced. So this is the questions that you normally raise in the abstract problem. Okay. So what is the basic question that we want to address here? We want to study, convergence of such functions. So you have a class of functions here, and you may have a sequence of functions fn from x to y. X has certain structure. Now, if you have sufficient machinery to talk about the convergence, which needs some structure on x, some structure on y, then we can talk about convergence of the sequence. Okay. So does it really converge to some function? Now this is one of the questions that usually one asks. Okay. But one of the problems that you encounter in this context is that, suppose in the basic structure of the space itself, X. So you may have a sequence Xn containing X. Now we assume without loss of generality that there is a facility called metric or a distance function on X, so that you can study the distance between various points in X. And suppose you have a sequence. Now when do you say the sequence converges? So we look at this problem. Xn converges to X. Okay. What does it mean? Assume X belongs to X. For the time being, belongs to this, and you take Xn is containing this. What do you mean by this? The meaning of this is that d of goes to 0 as infinity. Or in other words, xn gets closer and closer and eventually collapses with the point x. So you have an infinite sequence of points which converges eventually to x. I mean, your experience of working on the real line. For example, you take then you take the distance as the usual distance that you have. Okay? Then you say R is a metric space. And this is called a metric. Or distance measure. Okay, we will be more precise on this soon. Okay? Now let us look at the sequence one by one. So you ask the following question: what happens to limit n tending to infinity 1 by n? And you know that from your elementary calculus that this is equal to 0. So actually 1 by n converges to 0. But you would have done something very more sophisticated, that sigma 1 by n does not converge. What do you mean by this? So you take Sn, you define as sigma n equal to 1 to capital N. You say that what is the limit of this, or what is the sum that you have n equal to 1 to infinity of this, if at all it exists. This is going to be, so your question is this: limit n tending to infinity of Sn. You see that it doesn't converge at all. For that matter, if you look at the sequence n, it's a sequence in R, it doesn't converge. Okay? It just shoots off. Or even this one, if you take the sequence minus 1 to the power n. What is this sequence? This sequence is minus 1, 1, minus 1, 1, etc. So this is the sequence that you have, and this does not converge at all. So we have seen this several sequences and several series which converge or diverge, or all these cases you have been familiar with it from your calculus. So here you see that the sequence 1 by n converges to 0 that you have. The same question, suppose you take x to be 0, 1. Okay? X to be equal to 0. Now look at the sequence. You know that this is contained in 0, 1. There is no problem. Okay? What about the limit of this? Does it converge? It does not converge. In X, because in R it converges. In R it converges to 0 because 0 is an element there. But 0 is not included in your space X. Okay? So it doesn't converge on the set X. So there may be, see, even the structure of, or the very nature of your space also plays a role in convergence. Okay? So there may be several sequences which converge in this space 0, 1. But there may be some sequences which may not converge there at all, in spite of the fact that they give an impression that they are going sufficiently closer to get a limit. Okay, so to take care of this, we use the following criteria. So this is called Cauchy's or Cauchy convergence. Okay, let's see like this. So xn converges to x if this is, so that we have already had. We say that a sequence limit m n going to 0 of distance between equal to 0. Or as m and n tends to infinity, d of xm xn goes to 0. What is this? This is the distance between xm and xn. And as you go ahead with the limit as m or n tends to infinity, or it is equivalent, this is also true. You take limit n tending to infinity, d of x n plus k goes to 0 as n tends to infinity. You can make it more rigorous type of definition and look at this problem. So you see that in this context, you will see that the sequence 1 by n sequence which does not converge in 1, 0. So this is a Cauchy sequence, but it's not a convergent sequence on this interval. Okay, whereas on the whole bar it's a convergent sequence. Now what one can prove is that every convergent sequence but the converse is not true. Converse is not true, as we have seen that if you drop 0 from, if you do not include 0, then you see that there exists a sequence which is Cauchy, which is not convergent in this sequence 1 by n. Okay. So Cauchy sequences form a larger class, and you see that it is the convergent sequences form a subclass of that in general. Okay, so in some cases, every Cauchy sequence you may have a space. It's a property of the space that every sequence, every Cauchy sequence is a convergent sequence. So what you have is this. So you have the collection of all. This is Cauchy sequences. This is in general convergent sequences. Convergent sequences. So every convergent sequence is a Cauchy sequence, but a Cauchy sequence may not be a convergent sequence. Okay? I wrote it. Sorry. See that you have. Okay. Every convergent sequence is a Cauchy sequence, but a Cauchy sequence may not be a convergent sequence. So this has something to do with the space, as you have seen in this example. The structure of the space matters. In fact, one can prove that. I want to prove of this. That if you take a closed bounded interval, if x is equal to closed bounded interval, and you take any sequence xn since it's a property of the space, we say that the space is a complete metric space. So essentially, it will contain all those points with the property that so that all Cauchy sequences with elements in that space is convergent. Okay? I would also like to use the word for Cauchy sequence. I would also like to use the word that all convergible sequences. That is, all convergible sequences are convergent in that space. Now, this is what we do. Okay, what is the problem that we are going to consider next? Right. So we come to our problem. This is just some preliminary for this. So such spaces are called spaces D, property that all Cauchy sequences are convergent Therefore, you see that the whole of R is a complete metric space. So R is complete. But Q is not complete. Suppose you take Q with the distance function, the usual distance. Okay? Then you can construct actually sequences which converge, which possibly converge in R but not in Q. For example, you take one. Okay, so you know that E equal to 1 plus 1 by 1 factorial plus. So we consider the sequence Sn equal to 1 plus 1 by 1 factorial 1 by n factorial. So you have now a sequence S0, S1, etc. What about these numbers? They are all rational numbers. Okay? So this is a sequence of rational numbers, but you see that it converges, it does not converge to a rational number. It in fact converges to the number E, where E is not a rational number. Okay? So that is something that's right. Therefore Q is not complete, and in fact if you have seen the construction of R, what one does is really to go for all those missing points, so that eventually the space that you get is one where all convergible sequences do converge to some point in the space, and when you do that you get the completion of Q, namely R. Okay? So that's just to recall some of these points, just to brush up your mind. Okay. So what is the problem that you have? Quite often you deal with function spaces. Okay? It's a generalization of these kind of ideas. Okay, let me make some noise about what is this metric. Okay, you look at X. X is the basic space and D is the metric. Okay, what is metric? So this actually, you see that D is a map from X cross X to R plus union 0. Or this is expressed by saying that D of 0. What about the next feature? The next feature is that D of equal to 0. So this is actually this is your X, and we are talking about the distance between 2 points. I mean, not necessarily this. I mean, this distance. This is X and Y, and this is the distance between the 2 points. I mean, you know, I just need not be the straight line distance. It could be quite a lot of different things. Now, the distance of xy. The distance from x to y is 0, implies x equal to y. The third property that you need is you have for this function is that d of the distance from x to y is the same as the distance from y to x, that is symmetric. The fourth property is what you call the triangular inequality. Okay, that is the distance from x to z or x to y is less than or equal to distance from x to z plus distance from y to z to y. It is expressed by saying that you have to travel more distance if you want to go from x to y via z. Okay, where z is. I mean, maybe sometimes it could also depends on the position. So, but in general, certainly it is not less. Okay, that's like the fourth criteria. So, distance is a non-negative function. It is 0 whenever x equal to y, and if and only if x equal to y. And it's symmetric in the sense that the distance from x to y is the same as distance from y to x, and distance from x to y is less than or equal to distance from x to z plus distance from z to y. So if d is such a function defined on x cross x, then you say it is a distance function. Okay? and you see that R with modulus of x minus y is a distance function. Okay. Now we can define some exotic. For instance, even this is true. See. So suppose I take R and define d theta from, or I can take any x non-empty. Then I define d of xy to be equal to 1 whenever x not equal to y and equal to 0 whenever x equal to. Suppose I define this. This is the definition. Then I leave it to you to define this. This is what's called the discrete matrix. Okay? So you say that everyone knows only oneself in a gang of people and not others. Okay? So whenever x is not equal to y, there is a distance between the two integers. Otherwise, it is 0. That's quite easy to prove that this is a metric. So there are various metrics that we can define. For instance, on R2, you can define the following: d of, say R2 each point x I write as x1, x2, y as y1, y2, and let me just define this to be equal to sigma of x1 minus y1 to the power p plus y2 of p to the power 1 by p. Less than or equal to p, less than o. You can show that this is a metric. I mean, you need to do a little bit of work. And in particular, you see that when p equal to 2, this is the usual distance between x and y is the Euclidean distance. Okay? Right? When p equal to 1, what you get would be, the distance would be this one. This is the distance. Okay? Right? And then of course you have some d infinity, xy, you can write this as maximum of this is also a distance. So I write this d infinity. Okay? Yeah, in R2. And more or less on so all these things you can prove, try to prove, and it needs some hard work. And if you have done that, then in general on Rn, so you take the space Rn, which consists of all n tuples. usual structure of Rn. Then on that you define X, you define as Y, you take as Yn. Then you can define distance any one of this. You can take sigma I equal to 1 to k equal to 1 to n. To the power c. For each p, this defines a distance, and when p equal to 2, you get the Euclidean distance. And d infinity is a direct generalization of what I wrote there, defined as maximum of these are all various distances that you can define on Rn. Okay, with any one of this, it is a metric space. Use the right kind of distance function to work with your comfortably with your problem. That will be the mode of choice of the distance function. And then of course there are a lot of results related to that, which facilitates this. Now what we do is we try to generalize these to function spaces, and I think this is the right stage where I can stop it, and then in the next lecture I will take up the following. I will consider on the interval AB, take the class of functions CAB, all continuous functions on the interval AB, all Riemann integrable functions on AB, and endow this collection of objects with certain distance function and examine the problem of completeness, namely whether Cauchy sequences of in such spaces do converge in that or not. So that will be our major problem that we look at. Okay, and we take some results which are quite relevant to the questions that we are asking. Okay, thank you very much.